This exercise will introduce some tricks for creating contour maps of sparse groundwater elevation and concentration data. We'll start by opening an RWDAT file within the RockWorks datasheet. Click on the Project Manager tab. Expand the list of datasheet files by clicking on the arrow to the left of the Datasheet Files group heading. Scroll down to the Maps Sparse Data.rwdat file and double-click on it to open it within the Datasheet tab. We'll be using this data to demonstrate some of the different methods for contouring data. Let's start by selecting the Triangulation Contours program from the Utilities Maps pull-down menu. Unlike the other examples within this exercise, this program does not generate a grid model in order to create a contour map. Instead, it creates a network of triangles that connect the control points using a method called Delaunay triangulation. These triangles are then subdivided to create the contours. Start by setting the input to the proper datasheet columns for the easting and northing columns. Choose the GW elevation for the Z or elevation column. Click on the Triangulation Contours tab and then click on the Contours sub-option. Enable the colored intervals, set the scheme to min to max, and set the interval type to gradational automatic. Enable the contour lines and set the intervals to regular. Turn on the map overlays and enable the point symbols. Activate the Uniform Raster Symbols option. Click on the symbol icon. Select the symbol that you want to use to depict the control points. Set the symbol dimensions to fixed at 5% of the project size. Turn on the symbol labels. Click on the Content tab and enable the Northeast Label option. Select the GW elevation column for the Northeast label and disable the Fill option. Enable the Peripherals option and turn on the color legend. Turn on the border and click the Continue button. An angular contour map, similar to this example, will now appear within the new RockPlot 2D tab. As previously mentioned, this tool uses simple triangulation to create the contours without performing any grid interpolation. To view the triangles on which this map is based, click on the Options tab. Select the Triangulation Contours tab, turn on the Triangle Network option, and click on the Continue button. As shown by this diagram, the intersections between the 3D triangles and horizontal planes at each contour interval define the contour line segments. For some applications, this may be all you need to create a reasonable map. However, it will often be necessary to create grid-based maps with smoother contour lines that extend beyond a convex polygon that encloses the control points.
In this exercise, we'll switch to using groundwater elevations that are stored within the Borehole Manager because it provides more flexibility for using data for specific time periods. Before we get started, please note that the depth-to-base entries are optional because we'll only be paying attention to the potentiometric surfaces. Select the Plan Map option from within the Borehole Operations Aquifers pull-down menu. Click on the drop-down menu button and select Aquifer 1. Activate the Superface or Top Elevations option. Check the box adjacent to the Time Filter tab. Set the time filter setting to Exact. Set the exact date to 2/14/2017. So now the program will only use the Aquifer 1 upper elevations that were sampled on 2/14/2017. Click on the Main Options tab and select the Modeling options. Make sure that the model dimensions are set to use the project dimensions. Select the Algorithm tab to display a list of the available modeling methods. Choose the triangulation method, which is a variation of what was used within the previous exercise, except that the triangles will be subdivided into grid cells. Activate the Interpolate Edge Nodes option to force the surface to cover the entire project area. Activate and click on the 2D Grid Map tab. Turn on the colored intervals, contour lines, labeled axes, and map overlays. Click on the Map Overlays tab, activate the Borehole Locations option, and turn on the symbols and borehole IDs. Finally, click on the Continue button. A contour map depicting the Aquifer 1 surface grid will now appear within a new RockPlot 2D tab. Let's compare this surface model with other grids that use different interpolation methods to model the same data. Click on the Options tab and change the algorithm to kriging with automatic variography. Click the Continue button. The kriged model is similar to the triangulated model, but there are some significant differences, such as the saddle within the triangulated model versus the projected ridge within the kriged model. Let's look at another algorithm. Reselect the Options Algorithms tab, pick the radial basis function, and click the Continue button. Let's try one more. Select the Options Algorithms tab, pick the Trend Polynomial Automatic option, and click the Continue button. As with the other models, the trend polynomial surface is quite different. So which algorithm, and RockWorks has several more, is the best? At the risk of sounding snarky, that's like asking which one of these tools is best. This device is not very good at removing lug nuts. This device is not very good at exposing a fresh rock surface. This device is not very good at measuring the orientation of a bedding plane. Triangulation is great for modeling polygonal surfaces such as Monument Valley topography or engineered surfaces such as open-pit mines. Kriging excels at modeling geochemical veining and fractured rocks. The radial basis function, or RBF, is well suited for modeling compacted buried surfaces because it minimizes the curvature of the surface patches between control points. Trend surface polynomial fitting is a great tool for identifying regional trends and projecting surfaces into frontier regions that lack control points. For more information about the strengths and weaknesses of the various RockWorks algorithms, as well as the miscellaneous sub-options, click on the red Help button and search for Gridding Methods.